Hello everyone, and welcome to this video podcast for human genetics. This will be our second video podcast on population genetics. In the last one, we introduced a lot of the terminology and the ideas behind populations and studying the genetics of a population. In this podcast, I'm going to introduce you to the Hardy-Weinberg equilibrium and the equations that support it. And then we're going to talk about the assumptions of it and what happens when those assumptions are not met. A bit of a spoiler alert, when they're not met, we get evolution. All right, well, let's go ahead and get started then. Okay, now I'd like to begin this discussion of a very important concept called the Hardy-Weinberg equilibrium. It came about, at least in part, due to a misunderstanding of, or a misinterpretation, I should say, of Mendel's rules. There were many people at this time who claimed that dominant traits would become more common while recessive traits became more rare. Maybe at first glance this makes sense because we kind of have this bias thinking that dominant traits are somehow better, or there are some kind of advantage to a dominant trait. But Hardy was, from what it appears, was a little irritated that biologists were making this assumption because Hardy was a mathematician and he said the math doesn't work. He argued that recessive traits would persist. So Hardy, let's just put it down like so, he argued that recessive would remain in a population. And he would have also argued there's no reason to think that they might not become more common than a dominant trait. He felt comfortable saying this because he knew that mutations would introduce, or maybe reintroduce, recessive alleles in a population. He also knew that migrations, individuals moving into a population, that migrations would bring recessive alleles into that population. He also would have reasoned that natural selection may favor a recessive trait. It may be that some recessive trait has some advantage. And linked to that, we shouldn't forget to mention that recessive alleles, I'm going to say hide, they hide in heterozygotes. And we're going to talk in a moment about some of the equations associated with this concept, but it's safe to assume that this idea is dead wrong. There is no reason to think a dominant trait will be more predominant in a population, and there's no reason to think that a recessive trait will be lost from a population. I'm not saying it couldn't be, but there's no reason to assume it will because of some of these ideas down here. So I'm going to talk about two of the main equations for Hardy-Weinberg in just a moment. We will use them to explain an idealized population that's in the Hardy-Weinberg equilibrium. And what we mean by that is that a population that's in Hardy-Weinberg equilibrium is a population in an idealized state where allele frequencies in that population do not change from generation to generation. I want to stress this word here, idealized. In general, we don't think of too many populations being in Hardy-Weinberg equilibrium because we predict that allele frequencies will change, that recessive alleles and dominant alleles will have a change in frequency because of things like mutation, because of migration, because of natural selection, because of genetic drift, because of all these factors. So when we write this, we are describing an idealized state. Their equations are describing this idealized state. And so let's write some of these equations. The first one is P plus Q is equal to 1, where P is equal to the frequency of dominant alleles. And Q is equal to the frequency of recessive alleles. So what's nice about this is if you know the allele frequency of either P or Q, then you can determine the other one. For instance, if we know the frequency of P, that is the frequency of dominant alleles is, say, 0.7, then we know that the value of Q has to be 0.3, because this equation states that all of the alleles in a population have to equal 1. The next equation I want you to know is P squared plus 2PQ plus Q squared is equal to 1. In this, P squared is equal to the proportion of homozygous dominant individuals in a population. Q squared is the proportion of homozygous recessive individuals. And 2PQ is equal to the proportion of heterozygotes in that population. Again, looking at this equation, if you knew the value of P, and let's go back to 0.7, then you could make the prediction of all of these others. So if in a population you knew that the frequency of the dominant allele was 0.7, then you would make that prediction that the proportion of homozygous dominant individuals would be 0.7 squared, which would be equal to 0.49. We would know Q squared because Q is going to be equal to 0.3, so 0.3 times 0.3 is 0.09. Then you go 2 times 0.7 times 0.3, and that's going to be equal to 0.42. And if we add all of these together, we get 1. So by knowing the allele frequencies, we can use the Hardy-Weinberg equation here on top to determine the proportion of each group of individuals in that population. And we're going to work on another problem like this later, just to give you some more practice. Oh, but let me write down here what we had. 0.49, 0.09, and then 0.42. So how can we use this equation with Hardy-Weinberg equilibrium? Well, what we'll say is that these proportions, and when I say these proportions, I'm talking about these right here, will not change from generation to generation if Hardy-Weinberg, abbreviated there, assumptions are met. So what are these assumptions? Because that's kind of important. We've already talked about them, and we just talked about them in a slightly different context. But let's consider them again. So here I'm going to write Hardy-Weinberg assumptions. One of those assumptions that must be met to maintain this Hardy-Weinberg equilibrium is no mutations are occurring. Now, it doesn't mean no mutations in the entire genome. It means no mutations in these alleles we're talking about. No migration. That population is isolated, meaning individuals are not moving into this population we're studying, and individuals are not moving out of the population. No genetic drift. No genetic drift. And when I say no genetic drift, what I'm saying here is that it's a large population. Small populations are more likely to show genetic drift. And we'll spend a little more time talking about genetic drift later. So for a population to be in Hardy-Weinberg equilibrium, it has to be a large population to avoid genetic drift. This fourth assumption is mating is random. And the last one, it's kind of a big one here, no natural selection. These sound remarkably similar to what we showed a couple whiteboards ago, where we said that allele frequencies have to change because these things do occur. So this is just kind of reversing it. We're saying that a population is in Hardy-Weinberg equilibrium, this idealized state, because there's no mutations, no migration, no genetic drift, mating is random, and no natural selection. Now, in one sense, you might think, why are we having this somewhat elaborate equation here to describe a situation that perhaps never exists or rarely exists? What we can do, and we won't in this class, but what a population geneticist can do is they can take this equation and modify it when they know mutations are occurring, when they know migration or genetic drift or any of these other assumptions are part of that population. They can modify this equation to consider these variables. And by doing so, they can come up with very accurate predictions on how allele and genotype frequencies will change from one generation to the next. And that's really the goal. A population geneticist wants to predict how that allele frequency changes. We'll talk a little bit about that, but we won't worry about how we modify this equation. But you should know that the equation can be modified to take care of these assumptions. Now, earlier, I wrote a little example equation down here in the bottom left corner explaining how you could make predictions about the genotype frequencies if you knew the allele frequencies. I'm going to flip that now, and I'm going to ask us to solve this problem. The problem of, can we predict allele frequencies from a genotype frequency? And the answer is yes, of course, because math lets us do many things. So let's talk about the recessive trait of sickle cell anemia, where big S is the dominant allele and little s, which I'll underline to show it being little s, is the recessive allele. And let's say within a population, we know that big S is equal to 0.81. And that's all I tell you. And I ask you in a question, tell me the allele frequency of big S and the allele frequency of little s. And the first thing I'd recommend that you do is write the Hardy-Weinberg equation. P squared plus 2pq plus q squared equals 1. And remember, S is equal to, big S is equal to P, and little s is equal to Q. And we want to know what those frequencies are. I remember when I was first given an equation like this, I thought to myself, there's no way you can do this. It's going to take some kind of magical voodoo math, but it's not so bad. Since we know this value here is 0.81, we know that's the same as P times P. And so if we just take the square root of 0.81, which is equal to 0.9, we know that that is equal to P. When you get a question like this, take the square root of what the percent of homozygous dominant individuals is, and that's your value for P. Because remember, this now says if P is 0.9, and we went 0.9 times 0.9, it would be 0.81. So we know that P is 0.9. The frequency of big S in this population is 0.9. Pretty high, in fact. Now we have to get the value of Q. And so now we're going to look at the other equation. P plus Q is equal to 1. If we know P is 0.9, then we know Q has to be 0.1. And if you wanted to convince yourself again that this is correct, you could feed these into this larger equation. 0.9 times 0.9 is 0.81. 0.1 times 0.1 is 0.01. 2 times P times Q is equal to 0.18. And that is equal to 1. And again, what we would say is that this population, from one generation to the next generation, will remain at this frequency if those 5 assumptions are met. However, if any of those assumptions are not met, you would make a prediction that these frequencies would change. And so we know with a disease like sickle cell anemia that natural selection has played a role. Because we know with sickle cell anemia that heterozygotes, big S, little s, are protected against malaria. This natural selection component now provides an argument to have more Qs in the population. And if malaria is introduced into a population by, say, mosquitoes, one would predict that these numbers would change. How they would change, I don't know, but you would predict that Q would no longer be 0.1, but you might make a prediction that Q is going to be greater than 0.1, because there's a natural selection advantage to having more little s in the population. So that's kind of how you might use one of these equations. We thought about an idealized situation, and this is what it would be, but we throw in natural selection, and now we see that those frequencies would change. Now, on a test, I'll give you a hint, but if I ever give you a problem like this, where I tell you the proportion of homozygous dominant or the proportion of homozygous recessives, I will always use a perfect square so that you can do the square root of it more simply. What I'd like to do now is spend just a few moments talking about those 5 assumptions and how they will affect the allele frequencies. Now, as I said before, we're not going to talk about how we add to the equation to make the equation better, but I do want you to be aware of how these things, these 5 assumptions, when they're not met, how they do affect allele frequencies. And so the first one I want to talk about is non-random mating. So if in a population you had these individuals, and under Hardy-Weinberg assumptions, one would predict random mating. So each of these individuals would be likely to mate with each possible individual. And the result, if it's in Hardy-Weinberg equilibrium, in fact, let's go ahead and put that here, Hardy-Weinberg equilibrium, is that after a generation, you should still have the same proportions. You might have more of them because they've mated, right? So they've increased their numbers, but you see about the same proportions. And that's because of random mating. Now, if at some point it shifts to more of a non-random mating, so here, might as well put it here, this is random mating. But if I say Hardy-Weinberg equilibrium, I already mean that. So if we violate this assumption, and now there is non-random mating, we would say it is not in Hardy-Weinberg equilibrium. Now, let's say for whatever reason that in this population, the green individuals who are characterized by having the same allele sets, those individuals are more likely to mate with each other. It's no longer a random mating. The like individuals, in this case the green individuals, are more likely to mate. Now, this really isn't all that surprising because we know that in many populations, mating individuals often share some characteristics. They're not identical, but they might share some characteristics because that's why maybe that individual likes the other individual. There is a characteristic that is similar. Now, if in this population, individuals who have the green allele sets are more likely to mate with each other as opposed to mating randomly with anybody, then there will be more of that green allele set in the next generation. So this is a way that non-random matings, because you have individuals mating that are similar, that is a way you will change allele frequencies in a population and cause that population to fall out of Hardy-Weinberg equilibrium. The clinical side of that can lead to some problems is that it's a way that recessive mutations can accumulate. Doesn't mean they have to, but they can. Because remember, recessive mutations are often hidden in heterozygotes. So if we think about cystic fibrosis, for instance, this individual is protected, big C, little c. They're not going to have cystic fibrosis. But if in a group of other in that population, if they share certain traits, it might be that they also share this trait of being heterozygous for cystic fibrosis. That may manifest in some other way, perhaps. And because of that, you may end up with more progeny that are little c, or big C, little c. And you may see, so we'll go an up arrow there to show more of those, and you might see fewer of the big C's. Non-random mating is a huge contributor to changing allele frequencies. Let's now talk about migration. Remember, for a population to be in Hardy-Weinberg equilibrium, there can be no migration. And so migration is one of these factors that if it occurs Hardy-Weinberg equilibrium fails. So let's draw our 4 individuals in this population. They're not really individuals. These just represent 4 distinct allele combinations. And like we said on the last whiteboard, if they're in Hardy-Weinberg equilibrium, and in this case there would be no migration, you would expect roughly the same number of each of these allele frequencies in the next generation, and the next generation, and so forth. Now remember, as we've said numerous times, Hardy-Weinberg is an ideal state, and so we would expect it to fail at some point. And in this example, what we're saying is migration happens. And so if migration occurs, we can say falls out of Hardy-Weinberg equilibrium. And so let's say individuals entering into this population, let's say we get some more orange allele combinations entering the population, and maybe some more blue allele combinations entering that population. These individuals are now going to bring in more of those alleles to that population, and so it's not surprising that this addition is going to skew the next generation, where you're going to have, in this case, more blue allele combinations and more orange combinations than you would the green combinations or the pink allele combinations. All because we had these 2 allele combinations entering into the population. So an interesting example is this disease called galactokinase deficiency. And I'm not going to try to attempt to draw a map of Europe. You're welcome. But what I do want to say is this about this disease. In Germany, now I'll put Germany here, this deficiency is found in approximately 1 in every 57,000 individuals. In Switzerland, it's found in about 1 in every 2.2 million individuals. In Bulgaria, which I'm going to put down here, several countries in between, so it's a little further away, it's found in about 1 out of every 1,600 to 2,500 individuals. So more common here. So why is Switzerland so much more protected against this disease? There's probably been fewer migrations between these 2 countries because of those mountains, the Alps, that are in this region. It's protected individuals here from that particular deficiency. So when you start seeing more migration between these 2 countries, then you're going to see the numbers change. For instance, if more people from Switzerland move to Germany, one would predict this ratio would change. Fewer people would be affected with galactokinase deficiency if that were the case. Maybe if more people from Germany went to Switzerland, you'd see more people with that deficiency. If more people immigrated to Bulgaria, then perhaps you would see a decrease in this deficiency in this area. Next, I want to talk about genetic drift. Again, this population remains in Hardy-Weinberg equilibrium, and in this case we're saying no genetic drift. And as an example of this, we said no genetic drift might mean large population. So if this was true, it may remain in Hardy-Weinberg equilibrium, and you would expect to see the same proportions of individuals, or same proportions, I should say, of genotypes in this next generation. And as long as it stayed in Hardy-Weinberg equilibrium, it would always have the same proportions of genotypes, or of allele frequencies. As we've said once or twice, or perhaps 100 times, this doesn't usually happen. Things fall out of Hardy-Weinberg equilibrium frequently. So let's say in this case, genetic drift occurs. And so when genetic drift occurs, it falls out of Hardy-Weinberg equilibrium. And in this case, because of a smaller population, by some chance. For some reason, we don't know why, but let's say these individuals are no longer part of this mating population. They died for some reason. Maybe there was a war. Maybe a meteorite hit them. I'm not sure what happened. But for some reason, these individuals are no longer part of the population. And as a result, the mating population that remains is smaller. And so in this next generation, as this is written, one might expect to see a larger proportion of the green genotypes, same with the blue ones, there's fewer of the pink ones here, so one might predict you're not going to have as many. All of the orange genotypes are gone. So they won't even appear here, so I won't even draw them there. This is what happens with genetic drift. Now, there are two types of genetic drift I want you to be aware of, and the first one that we just described here is called a bottleneck. And all a bottleneck means is that, just what we explained, part of the population are no longer part of the reproducing part of this population. Now, the other example I want to talk about is something called the founder effect. It is also another type of genetic. Now, with the bottleneck effect, remember, we were removing part of this population. But the founder effect is a little different. The founder effect says that a small part of this population breaks off. So the founder effect is a little different, but has the same result. With the founder effect, a small part of the population breaks away, and they found a new population. And so now, any recessive mutations that happen to be in this small population that breaks away are going to be magnified in this next new population. And the way I drew this was pretty extreme because I only drew two existing genotypes here. But due to the founder effect, this next generation is going to have a large number of these blue genotypes. We'll have some of the green ones here, but most of them are going to be of this blue type of the individual here. So we call that the founder effect because they found this new population. Next, I want to talk about how mutation affects Hardy-Weinberg equilibrium. So we're going to start off with our same individuals here. So as we've said before, as long as it's in this Hardy-Weinberg equilibrium, we should see the same number of alleles in the next generation here. But it can easily fall out of Hardy-Weinberg equilibrium with mutations. So mutations present. You could imagine that in this next generation, when a mutation occurs, and let's just say a mutation occurred in this individual, or in these alleles, I should say, and maybe in the orange ones here. And let's say the orange one, when it was mutated, it changed it into an allele that was like the blue one. So let's write that up here, that this mutation caused the orange alleles to become the blue alleles. But right now, just think about one allele being mutated, and now it forms the next allele. If you want to think about it in terms that we've talked about before, maybe this allele here is little a, and it gets converted back to big A. And so now it's a different allele. And in this case, it turns out to be an allele that's already in that population. So because of that, just think about the orange and blue ones here, we're going to see more of the alleles that contribute to this blue genotype here. And we're going to see fewer of the ones that contribute to the orange one, because some of them have been mutated to become blue, so to speak. Green here is also going to remain roughly the same, because they weren't affected in this mutation. Now, before we move on to the pink one, I want to remind you that when this converted over from orange to pink, that eliminated that from the allele frequencies, because now it's blue, or big A in this example. Now, this pink one, the way I drew it here, this allele here was not mutated, and so it's still going to be present in this next generation. But there's only one of it, so it's not going to be as strong as it was before, or it's not going to be as frequent. And let's say that this part of the population here, that mutation, caused it to form a new allele in that population. And so we've eliminated this one from the population now, the pink one, and we've introduced a new one. So now we have a population that has more blue allele combinations than any of the other ones. The green ones didn't change a whole lot. We have fewer orange and fewer pink, and we have a brand new one now, this purple one. So this is how mutation can change allele frequencies in a population. Okay, so let's think about natural selection and how that affects allele frequencies. If it's in Hardy-Weinberg equilibrium, that means no natural selection. And we would predict that in this next generation, the allele frequencies won't change. You might, as I've said before, you might have more individuals, but the frequencies of the alleles will stay the same because it's in Hardy-Weinberg equilibrium. However, natural selection may be one of the more important ones that influence allele frequencies, can change this. So, if we say natural selection happens, it will fall out of Hardy-Weinberg equilibrium. Maybe these allele combinations that make the orange, for some reason, are no longer able to reproduce. And so in the next generation, you're not going to see them. It may take a couple generations to get rid of that combination, but eventually it will happen. So we would eventually see those gone. These frequencies will still be about a 1:1 ratio here, but there will be more of them, relatively speaking, because the orange ones are gone. So that would be natural selection. For some reason, this allele combination was not selected for, and it could have been because they can't mate. No mating. Maybe they're exposed to some sort of chemical in the environment, and this allele combination with that chemical makes them sterile, but not these individuals. So it gives these individuals a selective advantage at reproducing to the next generation. Okay, now that we understand a little bit at least about how population genetics works and how different factors can change the allele frequencies, it's an appropriate time to talk about something called eugenics. Now, eugenics has a long history, and you've heard about it probably in other classes, but I think it's good to bring it in to this class as well. So eugenics is a societal program or a policy that attempts to control human reproduction. And ultimately, the goal of this would be to control the genetic structure of a population. Eugenics can be considered either positive eugenics or it can be negative eugenics, which we'll talk about in a moment. But positive eugenics creates incentives for those with superior traits, and we'll put that in quotes, to have more kids. Now, the big problem with this is who decides what's a superior trait. I might think something superior like short, bald, and nerdy, but other people might think tall, athletic, and with a full head of hair as being superior. It's really kind of a very interesting term here. And we know, because you know the history of the world, that this is not always taken in the right direction, or taken in a direction that considers humanity. Now let's talk about negative eugenics. And this side often brings out the worst in societies. And negative eugenics interferes with reproduction of those considered inferior. Again, I put quotes around inferior because who decides what's inferior? Now, eugenic policies often are based on only considering the genetics aspect, the hereditary components, and not environmental factors. I also think it's important for us to recognize some important points in history where eugenic policies were introduced and used. It's a long list, so I'm not going to include everything, but some important ones, I think. In 1907, the first eugenics law were passed in the United States. Some of you might be surprised to hear that. I'm not saying there weren't eugenics policies before this time, but this was a law in the United States that was passed that was based upon eugenics. And this law sterilized the disabled and male criminals. In 1910, the Eugenics Record Office was established in the U.S. This office collected a wide range of data from all kinds of Americans. In 1924, there was an Immigration Act that was passed in the United States. And what this did, it limited immigration of those considered, and this is their words, idiots, imbeciles, epileptics, and they had a few others that were on that list. Maybe at first thought, some of that might make sense, but again, who was determining what this meant? 1927, Buck v. Bell case was heard in the United States. And this is a Supreme Court hearing that essentially said, or validated, the forced sterilization of U.S. citizens. And some of the reasons they were sterilized might be that they had a child out of wedlock. It might be that they were illiterate. They couldn't read or write. Might because they were an alcoholic. These were all reasons why somebody could have been forcefully sterilized. And it was validated in 1927. And many of those laws stayed on the book until the early 1970s. So I'm going to erase this, but I want to remind you that from 1907 to 1927, we're talking about things that happened in the United States. In 1934, and if you know your history, you know what we're probably approaching here, Eugenics sterilization law of Nazi Germany took place. And their rules were largely based upon the U.S. policy. So early eugenics programs in Nazi Germany had their roots into our policies in the United States. And these early laws sterilized people for very similar reasons that we did. In 1939, as we all know, they took it to the next level and they took it to murder, where they began, I think the numbers are about like 5,000, you don't need to remember this, of children that were disabled, had some sort of birth defect. And eventually that rose to 70,000 unfit, whatever that means, adults. So yes, the United States was involved in some of these sterilization laws, but it was Nazi Germany that took it to that next level of murdering individuals based upon their genetics. In 1956, the U.S. reversed many of their laws, many of the sterilization laws. Some of them stayed in effect for up to about 1970 or so, but somewhere between, in this time, 50,000 to 70,000 Americans were forcefully sterilized. In 1990s, in the U.S., it became illegal for insurance companies to discriminate against genotypes. So if you were a carrier for, say, cystic fibrosis, they couldn't discriminate against you and your children for the possibility that you could be passing on this mutant allele. So this was a law that fought back against eugenics. In the 2000s, these laws were bolstered by the U.S. Genetic Information Non-Discrimination Act. It's limited in its scope, but it's a step in the right direction, I would think. Now, of course, some things don't change, and we still have bad things that happen. In 2004, genocide of black Africans in the Sudan. And there's certainly been other incidences of genocide that I could have mentioned here too. This is just one I'm pointing out. And it's good for us to think about the future. We have widespread genome sequencing available. If you watch the movie Gattaca, we're close to that, where you could perhaps know your genotype. Actually, that's pretty common, that we can know the genotypes of our own selves, but being able to make a prediction about what your children's genotypes are, and then potentially making choices based upon that test. That is, for the most part, solely only looking at the genetics, and failing to consider that the environment has a huge factor in many of these traits.